Okay, so this is page 2 in your new packet. Pause the video here and try these 5 problems as a warm-up. Now, when we do these questions, every teacher has their own strategy that they prefer, and mine for these exact values is to draw the special right triangles. So I will do that every time. If you have a different strategy, you can use that instead. So I like to get my standard special triangles down. I like to write my quadrants. None of these are quadrantal, so I'm not going to bother with my points around, but this will help me state the sign, positive or negative, of sine, cosine, and tangent in quadrant 1. So in quadrant 1, they're all positive. But in quadrant 3, only tangent is positive, sine and cosine are negative down here. That's 1, 2, 3, and 4. So now for the exact values, cosine of pi over 6, so here's my pi over 6 angle. I'm gonna go, cosine is adjacent over hypotenuse. And pi over 6 is in the first quadrant, so I'm okay with positive. Now tangent of 4 pi over 3, so here's pi over 3, and tangent is opposite over adjacent. But 4/3, if I think of this as 3 pi over 3, puts me in the third quadrant. So since it's tangent, it stays positive, the ratio stays positive. And now a negative 11 pi over 6, I don't like that that's negative. So I'm gonna find the coterminal angle by adding 2 pi. So 12 over 6 is 2. So that's the same thing as pi over 6. So I come over here, sine of pi over 6 is opposite over hypotenuse. That's 1/2. So our focus today is going to be graphing inverse trig functions and their domain and range. So page 3 first starts off, this is page 3, with some notation for us. So the -1 exponent stands for inverse. It's also the same. You can write that as arc sine, arc cosine, and arc tangent. And when we find the sine inverse or the cosine inverse or the tangent inverse, we think of it as what angle, or the angle that gives me the sine of x. So, for example, if we said tangent inverse of 1, that's asking me what angle gives me a tangent ratio of 1. And I like to, again, use my triangles. So out of these triangles, which angle gives me an opposite, because this is, 1 is the opposite over adjacent. So which of these triangles has an opposite and adjacent that are equal? And what angle gives me that? Is pi over 4. So these inverses undo the original. We're given a ratio and the output is an angle, instead of inputting an angle and getting out a ratio. So the next parts all go through everything that I'm going to verbally do for you on the next pages. So I'm not going to bother to go through that text. If you turn to page 5, I'm going to develop for you the sine inverse graph, and then we're going to do the domain and range based on what we graph here. If you are using a pen, please stop and switch to pencil, because we are going to erase a whole bunch of stuff once we get started graphing. So from our parent function of sine, I'm going to fill in my critical values. Let's go, whoa, sorry. I just smacked the iPhone holder stand, sorry about that. Let's go from negative pi through our critical values up to 2 pi. Then we're gonna add a box, add a box on here. So we know the sine graph starts at the origin, so at 0 radians, the y value is 0. At pi over 2, the y value is 1. At pi, the y value is 0. At 3 pi over 2 down here, we get negative 1. 2 pi is back to 0. We're gonna go backwards, that's negative 1 and 0. So when I go to, focus. Okay, so when I go to graph the inverse, we know way back from geometry and algebra 2 that it's the reflection over the line y equals x. And that's a long time ago. And there was a little trick we had when we would graph that, and we would switch the x and y values to plot the inverse. That gets me the reflection over the line y equals x. So my y values become the x values. So here's 1 and negative 1. And my angle measurements become the output of the y values. Remember I showed you that tangent example where x is the angle and y is the ratio? Well, now it's going to switch. X is the ratio and y, the output, is the angle. So I'm going to go positive pi over 2, positive pi, 3 pi over 2, 2 pi, then we're gonna go negative pi over 2, down negative pi, and I'm gonna stop there because that's where my table stopped. And this is the part, if you're following along with me, you have to use pencil because I'm gonna erase some of what I graph over here. So I'm gonna graph the point 0, negative pi, so over 0, down pi. I'm gonna graph the point negative 1, negative a half, that's right here. I'm gonna graph point 0, 0. I'm gonna graph 1 pi over 2. And I'm gonna graph 0 pi, negative 1, 3 pi over 2, and back to 0, 2 pi. So if I connect these dots, I get my inverse sine graph. However, the way it's graphed right like this, it's not a function. So the problem is I have to erase parts of this so it is a function. I'm not going to just erase where I feel like it. There's a standard domain and range, and I'm gonna take 2 sticky notes here. Give me a second to get rid of the sticky part. And I'm gonna highlight just sections of the graph so that we can see, is the graph a function or not? So for example, sorry. All right, if I make my range go from 0 to pi, this is not a function. This still does not pass the vertical line test. That's not gonna work. If I slide up, now from pi over 2 to 3 pi over 2 is a function, but that's kind of just floating. Like if I went from here to here, that's just floating in the middle of the graph. So instead of floating up here, what if I went from negative pi over 2 to pi over 2? Is that now a function? Yes, it is. So I'm going to erase below the negative pi over 2 and up here above positive pi over 2. And the official is supposed to be kind of curvy shaped. If you look at, go back to page 3, this is what we just graphed by limiting our wave that was that was reflected, excuse me. So the domain of the regular sine function is all real numbers. And the range, we know, goes from -1 to 1 of the parent function. Or you could say it this way. Oops. But now for the inverse function, the domain goes from -1 to 1. And the range is -π/2 to π/2. If I want to think of our unit circle, 0, π/2, pi, 3π/2, 2pi. If we go a negative angle back this way, instead of 3π/2, I'm going to call this one -π/2, so positive then negative. The sine inverse function then only exists over here in quadrant 1 and quadrant 4, because I get a group of positive sine values and a group of negative sine values right next to each other in our unit circle. Whereas if I stretch that out to the graph, I have this continuous function from -π/2 to π/2 on the range that comes from going clockwise and counterclockwise around the unit circle. So we're going to do that again for the cosine function. Here's cosine. We're going to go -π, -π/2, 0, π/2, pi, 3π/2, 2pi. Again, it's all our quadrantal angles. So the cosine graph at 0 has a y value of 1, and then 0, -1, 0, 1, then we're going to go backwards, 0, -1. And again, if you're using a pen, switch to a pencil, please. We're going to reflect our cosine graph to get the inverse. So my y values become the x values, the x values become the y on the scale here because of the reflection over the line y equals x. So -1, -π, 0, -π/2, over 1 up 0 here, over 0 up π/2, over -1 up pi, over 0 up 3π/2, and there's that last one. And honestly, I like connecting the dots this way better. I'm used to making my wave with my paper turned. And again, that's not a function. Cosine inverse is not a function when I graph every single value from the parent function. So let's see, if I take away this part, that's still not a function until I get to 0. So, got my eraser. I'm going to erase everything below the x-axis. Keep your labels of 1 and -1. And everything above pi. So this is so far down there. I'll just write it up here. So the domain and the range, the domain and the range. So the domain of the parent cosine function, the original, is all real numbers. You can put in any angle and get out a ratio. The range goes from -1 to 1, including those values. But now for cosine inverse, the domain goes from -1 to 1, that's our x's. But the range goes from 0 to pi. And if you think of the unit circle, from 0 to pi, this way, includes a quadrant that cosine is positive and a quadrant that cosine is negative. So 0 to pi on the unit circle, translated out or stretched out to a graph, 0 to pi, we get a function. All right, last but not least, we've got tangent inverse, negative pi over 2, 0, pi over 2, pi, 2, whoops. Add in a box here of 2 pi. And now I really should have included pi's over 4 because that's the value of 1 on the tangent graph. That's all right. Okay, we'll go with it. So 0, 0 at pi over 2 does not exist. That's an asymptote. That's here, sorry. At pi, we got 0 again. At 3 pi over 2 is another vertical asymptote. 2 pi is at 0. Going backwards, we got the same. Oh, I gotta do it. Let's put some pi's over 4s in here. Let's squeeze one in. So at pi over 4, which is right here, the tangent value is 1. Okay, so translating that to my graph, we now know we have to limit some of our domain and ranges so that, we have to limit the range so that the graph is a function. So if you're tired of erasing, just pause for a second. I'll tell you where to graph the final function. So we've got negative pi over 2 here with an asymptote that does not exist. And then our 1, then our negative 1 goes this way. Pi over 2. So when I get up here to 3 pi over 2 for the next asymptote, I see it's not going to be a function because I get these S-shaped tangent graphs in between the asymptotes. So this is too high. So we're going to be stuck between negative pi over 2 and positive pi over 2. And I know at positive pi over 4 here, the value is 1. I know 0, 0. So negative pi over 4 gives me negative 1. And I want to approach my asymptote. Oh, I missed the dot. That's all right. And I kind of get this sideways S shape, increasing the whole way from the asymptote through the origin. That looks a little bit better like that. Through this asymptote, and then, through that point approaching this asymptote. So the domain of the tangent inverse is all real numbers. It goes forever left and forever right. But the range, not including the asymptotes, is negative pi over 2 to pi over 2. Not or equal, which is why I do a rounded bracket. So now pause the video, finish your last tangent inverse. And let's fill in the domain and range of the original. So the domain of tangent is all real numbers, but x cannot be, how do I want to write it? I like n pi over 2, where n is an odd integer. So that's x cannot be 1 pi over 2, 3 pi over 2 for odd, 5 pi over 2. It can be even, so 2 pi over 2 is pi. That's right here. Another way, depending on your teacher, you could write it as all reals. X can't be pi over 2 plus k pi, because pi is the period where k is an integer. So you add 1 period, 2 pi periods, 3 pi periods, 4 pi, 5 pi, and so on. So either these are interchangeable, they mean the same thing. And the range of the tangent graph is all real numbers. Okay, before we get full-fledged into trig inverse functions, it's worth reviewing the inputs and outputs. And I've already stated this a little bit. The angle is your input. The output is the whole ratio. This y value is the whole ratio. The entire expression equals a ratio. With the inverse, it switches. We input the ratio. The sine inverse of a ratio gets me the output of an angle. So page 8 summarizes everything we just did. Use that as a resource. And page 9 is your homework. So you gotta sketch a graph, write the domain and range, sketch a graph, write the domain and range, and try to do it without looking back at the notes we just did. See if you can sketch the parent function and reflect for the inverse, sketch the parent function, reflect over y equals x for the inverse, and so on.